So let's just look at a convolution as a practical example, so it means a little more to you than perhaps this formula that I showed in the last part. So the convolution operation is between two functions f of x and h of x. Looks something like that. It's an integral where you flip h and you shift it by x, and then you look at the integral of the product of the two. So let me just show this as one example. So let's suppose you want to take the convolution g of x convolved with h of x. Let's take a simple function. Let's take two rectangle functions. Let's take a rectangle function like that. Let's just say it goes from -1 to 1, and it has some amplitude a, and that's f of x. And then we have h of x is identical. It's another rectangle function. So that's g of x. And now the first thing we need to do is we need to f of x times h of big X minus x dx. So the first thing we could do is we set big X to 0, so there's 0 shift, and so we just take h of minus x. So that's actually the same thing as flipping that function. But of course, for a rectangle function, g of minus x is the same as g of x. So, but let me just draw it anyway. We're gonna stick with the rectangle function, but it's not very evident what flipping means. So what I thought I'd do is I just quickly plot on top of this another function where flipping does make a difference. I mean, it's not what the example we're going to use right now, but let's suppose I take this function. So it goes up, and so this particular function here, when you go to g of minus x, I'm sorry, this is h, by the way, so please, this is h. G is what we call the convolution function. So the convolved function is f of x convolved with h of x, and h of x has this shape here. So rectangle, rectangle. But just to show you another function, we're actually, and this should be h of minus x. Now for that function, for the red one here, flipping each x to minus x would be the same as flipping the function over. So you have this original function, and you flip the function, and now what you do is you just shift. You shift h of minus x across f of x, and you take the integral at each point. So you work out the area at each point as a function of x. So let's do this. Let's try this out. So we'll try it with the two rectangles. So here we go. So let's plot this function. So we go from -1 to 1. So here's your f of x, and now my h of x, let's put this like this, 1, 2, 3, and 4. So let's make, so this is h of 4 minus x. So it's flipped. Of course, it doesn't look any different, but it's shifted by 4, right, from the origin. So originally it's at the origin, so they would be on top of each other. But let's just start at this position here. So this would be for x equals 4. Of course, you do this from -infinity to infinity, but this is one particular discrete position, just so you get the idea behind this. So x equals 4 on this particular point. And now let's reduce x. Let's make x equals 3. So then this would come over here. Then x equals 2 is there. So let's just do that. So here is this is, so you now come to here, and then for 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So here you've got x equals 3, x equals 2, and when x equals 2, they start touching. These two functions start touching, right? And then as I make x equals 1, they're actually overlapping quite significantly, and so now the integral is no longer 0, right? So it starts gaining some value as they start sliding across. So the value of this convolution will rise. And of course you keep continuing until you slide past, and then the value outside is 0 again. So what you will end up with in this particular case is you will see that as I slide across, the area will linearly increase until the two functions are right on top of each other. Then the integral is a maximum. And then you slide it further across, and then it will decrease again down to until it becomes 0. So what actually the function will look like, so the convolution g of x, the convolution g of, sorry, this is big X as a function of displacement will look something like that. It will so it will have a maximum at x equals 0, and it will go to 0 as x equals 2. So what you see is that the convolution operation gives you a triangle function. So the convolution of rectangle function with the rectangle function is equal to a triangle function. And in fact, the triangle has twice the widths compared to the original rectangle function. Right, let me just turn back to this example here. So the two rectangles, the convolution becomes a triangle function. And so if I go back to the convolution theorem, we can actually work out what the spectrum of this function is, of this new function. So it's now a function of the shift between the two original functions f and h. And the convolution tells me that the spectrum we get, of course, by taking the Fourier transform of this function here. So the Fourier transform of g of x is equal to the Fourier transform of the convolution operation between those two original functions. And we already know from the convolution theorem that that is equal to the product of the individual Fourier transforms. So now this convolution turns into a product. And that's actually very useful because we know that that is a sinc function, and we know that that is a sinc function. And so the spectrum of the convolution, i.e. the spectrum of the triangle function, is a sinc square function. And so you can see by knowing the spectrum of a simple function like the rectangle function, and knowing that another function is a convolution of two rectangle functions, I can immediately write down what the spectrum is, what the frequency components are of this new function from the convolution theorem, because it's trivially just a product of the individual spectra. And we can take this now and make good use of it by returning to a problem from a few hours ago, which is Young's slits. Except now we make this more complicated, so actually doing it our hard method, where we would work out the diffraction integral, the Fraunhofer integral, for the aperture function, which now consists of two slits. Rather than working this out explicitly and doing lots of math, we employ the convolution theorem. So now we do this via the convolution theorem. And so let's suppose we have two slits. We now, in Young's slits, we don't make them infinitely thin. We now let them have a certain width. So let's make them of width b. So the slit goes from minus b over 2 to b over 2. And let's have it, let's have the light field inside have amplitude 1. So this is my function f of x. That's x. And so that's one slit, but of course I have two slits, and the two slits, let's suppose the two slits are separated by a distance a from one another. Then what you know is that that is the actual double slit, looks like this. Each slit has width b. And they are spaced a distance a from one another. And in fact, this function here, by the convolution theorem, is just a convolution of this function with two delta functions. So one delta function at minus a over 2 and one delta function at a over 2. So that's minus a over 2 and that's a over 2. So that's a over 2 minus a over 2. Can you see this? So, so this is g of x. That's h of x. And so you can see that by convolving a rectangle function with two delta functions spaced a apart from one another, we get a set of two slits that are separated by a. And so if I want to know what the distribution looks like in the conjugate plane, so I have the two slits, the apertures. The conjugate plane is the image plane from the conjugate plane of the tube lens. That's where the pattern will be formed, the diffraction pattern. So in the conjugate plane, we just get the Fourier transform. And so the function, this function, you already know, is a sinc function. One rectangle is a, so if I go down this way, the Fourier transform of a rectangle function is this. So this would be 2 pi over b and 2 pi over b. So it'll look something like that. That's where the minimum is. That's the sinc. So this is the field. So it goes negative a little bit. The intensity is squared. So we're looking at the amplitude here. And then what is the Fourier transform of two delta functions spaced at a from one another? So we have, if you remember, it's e to the ik a over 2 plus e to the minus ik a over 2. So the only term that will remain is the cosine term, and so you get a cosine ka over 2. So you end up with a with a spectrum for this, which is cos k a over 2. And this here is the sinc function. And of course, in Fourier space, this convolution turns into a product. So the actual pattern now becomes a... So essentially, when you multiply these, you get a modulation of this function. So if I draw this like this, so you get a modulation of this function that looks like that. So that's the product of these two functions. And you know, you didn't have to do any math. This would have been really quite tricky to work out. And here all you need to know the Fourier transform of the rectangle function. You need to know the Fourier transform of two delta functions, which is just a cosine. And then you need to know the convolution theorem. And so you just need to know the individual, so you can work out what the individual spectra are for these. And then you have the overall spectrum of this function here. You can just write it down immediately, and that's what we will need when we go forward in describing the 4F imaging system in the microscope. So to just recapture, you can synthesize any function from its frequency spectrum. So for example, this rectangular function has this frequency spectrum. So if I add all these frequencies up with these amplitudes, then I will reproduce this function here. And we have seen that, that the microscope obeys the Fraunhofer conditions of diffraction, and then the diffraction integral turns into a Fourier transform operation, pretty much exactly. And so if we want to know what happens in conjugate planes, so if you have an aperture that's one focal distance away from the tube lens, and then you image that onto the image plane, then the operation between those two planes are exactly a Fourier transform of the function in one plane to the other plane. And with that, I finish lecture 7, and I'll see you in the next lecture.